With this video, we are beginning section 6.5, which is titled Calorimetry. We've been talking a lot about heat changes in reactions and processes, but we've never really talked about how do you measure heat change in a reaction. Well, you do it with a calorimeter, okay? And probably you've seen this already in lab, but it's a closed container designed specifically to measure heat changes. And if we're going to learn about how to measure heat changes, we have to understand specific heat and heat capacity. Specific heat is the amount of heat that's required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Heat capacity is the amount of heat required to raise the temperature of any given quantity of that substance by 1 degree Celsius. The specific heat of water is 4.184 joules grams Celsius. Now that's how much heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. But if I wanted to know how much heat it took to raise, let's say, 60 grams of water, then I would say, what is the heat capacity of 60 grams of water? In the table, I'm showing you specific heats of some common substances that we might be using. So basically, if we know the specific heat of something and the amount of the substance, then the change in the sample's temperature will tell us the amount of heat that was absorbed or released in a particular process. So these two equations that you see down here, Q, which is heat, is equal to ms delta T, and Q is equal to C, heat capacity, times delta T, give us a way to measure the heat changes in certain processes. If instead they give you the heat capacity and they ask you for the heat change, well then you would use the second equation. Q is equal to C times delta T. Let's do some problems. Alright, this is example 6.5 within the chapter. It reads, an iron bar of mass 869 grams cools from 94 degrees Celsius to 5 degrees Celsius. Calculate the heat released in kilojoules by the metal. So since they're asking me for the heat released, I am going to use the equation that we just learned. It's Q equals ms delta T. Because they tell me the mass of it, I can also figure out what the specific heat of iron is by the table, and they give me the change in temperature. So that should be a pretty simple calculation. So I write Q is equal to 869 grams times, I find what the specific heat of iron is, and you can see right there it's 0.444, so times 0.444 joules over grams times Celsius times TF minus TI, which is 5 minus 94. That ends up being negative 89 degrees Celsius. So basically I multiply negative 89 times 0.44 times 869, and I get a total of negative 34,339.404 joules. But they want the answer in kilojoules, so I move the decimal place 3 places to the left, and I get negative 34.3 kilojoules. All right, let's move on. Okay, so constant pressure calorimetry is used to determine the heat changes for non-combustion reactions. For example, acid-base neutralizations or heat of dilutions, heat of solutions. Here, I'm showing you a very crude example of what a constant pressure calorimeter would look like. And all it is, it's made up of 2 styrofoam coffee cups, and the outer cup helps to insulate what's reacting inside the inside cup. 2 solutions of known volume containing the reactants at the same temperature are carefully mixed inside the coffee cup. And then the heat that's produced or absorbed by that reaction can be determined by measuring the temperature change with the thermometer. You have to assume that no heat will enter or leave this. And of course, this is very crude, but for our purposes, we're going to assume that no heat enters or leaves this calorimeter. All right, so if I wanted to find the heat of the system, I've got to add up everything that's involved in here, right? So I've got water, I've got this calorimeter, and I've got whatever heat is evolving from the reaction. But I know that no heat should enter or leave this system. So I'm going to say that the Q system is equal to 0. And I would have 0 is equal to Q water plus Q cal plus Q of the reaction. Well, I want to solve for the heat of reaction. That leaves me with negative parentheses Q water plus Q cal. Right here I can stop because I know what Q water is. Q water we defined earlier. It was mass times the specific heat times the change in temperature. And I also know that this is constant pressure, right? So if it's constant pressure, then that means that whatever heat is coming out of this reaction or going into this reaction must be equal to the change in enthalpy. We're going to try some problems with constant pressure calorimetry, and you're going to see that these aren't very difficult at all. All right, let's do one. This is example 6.7 in your chapter. Before we start, I want to mention that I forgot to tell you in the last slide that when we do these type of problems, these constant pressure calorimeter problems, you can go ahead and neglect the heat capacity of the coffee cup. So remember how the Q system was equal to Q of the water plus Q of the calorimeter plus Q of the reaction? Well, we can go ahead and neglect the Q of the calorimeter because it's so small that it doesn't really make any difference. So just keep that in mind. All right, so the problem reads, a lead pellet having a mass of 26.47 grams at 89.98 degrees Celsius was placed in a constant pressure calorimeter of negligible heat capacity. See here, it tells you that you don't have to even worry about it, the calorimeter. All right, which this calorimeter contains 100 mils of water. They've got a lead pellet, it weighs this much, it's at this certain temperature, and you're gonna put it in this container that has 100 mils of water. That water started at 22.5 degrees Celsius, but then after you put the pellet in, it rose to 2317 degrees Celsius. So they want to know what the specific heat of the lead pellet is. The way to do these problems, the way that I do them, is I draw a picture. All right, so I do my little initial state and my final state. In initial, I've got this pellet, it weighs 26 grams, it's got a certain temperature, and then before I put the pellet in, I've got 100 grams of water, right, because it's 100 mils, but that converts to 100 grams of water because of the density, and it starts at 2250 degrees Celsius. But then after, the final stage would be that the pellet isn't inside the water, and now the water has changed temperatures to 2317. So here, my Q system would be made up of the water and the pellet. That's the two things that are going on here. But I know that since no heat enters or leaves, supposedly, this calorimeter, that means that my Q system can be 0. So then I've got the Q of the pellet plus the Q of the water is equal to 0. Well, now I have to basically solve for one of them because they want to know what the specific heat of the pellet. So I'm going to solve for the Q of the pellet. So Q of the pellet, which is Q of lead, is equal to negative Q of the water. At this point, it becomes easy because you can just plug in everything that we know. The Q of the water is equal to mass times the specific heat of water times the change in temperature. And then the Q of the lead is equal to the mass of the lead, which we know, the specific heat of the lead, which that's what we're solving for, times the change in temperature of the lead. The Q of the water is 100 grams times the specific heat of water, which is 4.184 joules per grams times degrees Celsius, times the change in temperature of the water. Well, the change in temperature is 23.17 because that's the final temperature of the water minus the initial temperature, which is 22.5. Multiply all that together, you get 280.3 joules. So that's the side of the water. Now we've got to figure out the side of the pellet. The side of the pellet is equal to the mass times the specific heat of the pellet times the change in temperature. The mass is 26.47 grams times S, because we don't know that, times the change in temperature of the pellet. The final temperature of the pellet is also 23.17 minus the beginning temperature, which is 89.98 degrees. If you multiply all that out, you get specific heat of lead being at 0.158 joules per gram degrees Celsius. That is basically how you do these problems. Let's start talking about standard enthalpy of formation and reaction. Before we talk about standard enthalpy of formation, let's do a recap. We've learned that the enthalpy change that accompanies a reaction can be determined by measuring the heat absorbed or released at constant pressure. And we also saw that the delta H, the change in enthalpy, can also be calculated if we know the actual enthalpies of the reactants and the products. However, I mentioned at the beginning that it's sort of impossible for us to measure the absolute value of the enthalpy of a substance because we really can't know the absolute internal energy or energy of a system. Your book gives you an analogy of how to think about this. The problem is similar to the one geographers face in expressing the elevations of specific mountains. Rather than trying to devise some type of absolute elevation, they basically take it from the sea level. Our Earth does not start at the sea level, but we can't go to the core of the Earth. So we set an arbitrary reference at sea level and we define that as 0. The sea level reference point for all the enthalpy expressions in chemistry is called the standard enthalpy of formation. Substances are actually said to be in their standard state at 1 atm, and hence that's the term that we use, standard enthalpy. The superscript little circle represents the standard conditions at 1 atm, and the subscript F stands for formation. So you have the change in the standard enthalpy of formation. By convention, the standard enthalpy of formation of any element in its most stable form is 0. So for For example, oxygen is a diatomic molecule. O2 is its most stable form, so the standard enthalpy of formation is 0. Ozone, O3, is not in its most stable form, and that actually has a value. It's 152 kilojoules per mole. The standard enthalpy of carbon in the graphite form would be 0. That's the most stable form of carbon. But if you do carbon in diamond form, that's not most stable, so it has a value of 1.9 kilojoules per mole. Based on these references for the elements, we can now define the standard enthalpy of a formation of a compound as the heat change that results when 1 mole of that compound is formed from its elements at a pressure of 1 atm. There's a table in your book on page 255 that lists the standard enthalpies of formation for a number of different elements and compounds. There's a complete list, though, in the back of your book in Appendix 3. So the importance of knowing the standard enthalpies of formation is that once we know those values, we can readily calculate the standard enthalpy of reaction, defined as the enthalpy of a reaction carried out at 1 atm. For example, consider this hypothetical reaction that I have here. A plus B produces C plus D, where the little a, b, and c, and d are the stoichiometric coefficients. For this reaction, the standard enthalpy of reaction is equal to products minus reactants. It's basically the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpy of formation of the reactants. There's two different methods to calculate standard enthalpies of reactions. There's a direct method and the indirect method. The indirect method uses Hess's law, and basically Hess's law states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. You are responsible for reading over the direct method and the indirect method of finding enthalpies of reactions. I will do them in class, but let me go ahead and just do one simple problem that deals with this. Alright, so this is example 6.9 in your chapter. It says, calculate the standard enthalpy of formation of acetylene, C2H2, from its elements. And then they give you these corresponding equations and their corresponding enthalpy changes. The goal is to calculate the enthalpy change for the formation of C2H2 from carbon and hydrogen. The reaction does not occur directly. It takes a couple steps to get to this. So we must use an indirect route using the information given to us in those equations, A, B, and C. So if we look at the synthesis of C2H2, we need 2 moles of graphite as the reactant. So we have to make equation A look like the main equation. So we multiply equation A times 2, you would have 2 carbon dioxide plus 2 moles of O2 going to 2 moles of CO2. Not only that, but you have to change the amount of the enthalpy of reaction. So now it's negative 393.5 times 2. And the reason we did this is because, again, our goal is to make it look like the main equation on the top. So we're done with the carbon. Next, we need 1 mole of H2 as a reactant. And this is already provided in equation B. So we don't do anything with that. The last thing we do is we need 1 mole of C2H2 as a product. So this is a problem. Equation C gives it to us as a reactant, but we need it as a product. So that means that we need to reverse the equation and divide it by 2 because we only need 1 mole of product. And they gave us here 2 moles as a reactant. So we flip the equation, which means that we reverse the sign of the enthalpy, and we also have to divide everybody by 2, which means we also have to divide the enthalpy value by 2. So we would end up with 2 carbon dioxide plus 1 mole of water yields 1 mole of acetylene plus 5/2 of O2. And the enthalpy of reaction ends up being positive 1,299.4 kilojoules per mole. Now, all we need to do is add the equations up, because remember, calculate the standard enthalpy of formation of C2H2. It's just a number, right? So we add up everything we have made so far. So it's negative 787.0 plus negative 285.8 plus positive 1,299.4 gives us an enthalpy of reaction of positive 226.6 kilojoules per mole. Therefore, the standard enthalpy of formation equals 226.6 kilojoules per mole. The standard enthalpy of formation value means that when 1 mole of C2H2 is synthesized from 2 moles of graphite and 1 mole of H2 gas, 226.6 kilojoules of heat are absorbed by the reacting system from the surroundings. And thus, it's an endothermic process. We did this problem with the indirect method, but there's also the direct method of problems, and you can do those on your own. All right, so that's it for chapter 6. Study hard, and I'll see you guys later. Bye-bye.